Hey, what's up, pre-calc students? This video is going to go over the 2.4 notes. Now, we already did the first two pages, so we're going to hop right to that third page. So on this page, we're just going to do a quick Algebra 2 review, just so that we could use these skills to find the zeros of our polynomial functions. So I just want to remind you that any quadratic equation, ax squared plus bx plus c equals 0, can be solved by the quadratic formula. And that formula was derived using a process called completing the square. And it will work on all quadratic equations. Now, if the quadratic equation is something that can be easily factored, it's always going to be faster to solve it by factoring. But rest assured, this formula will work on all quadratic equations. All right, next up are imaginary numbers. So in Algebra 2, you learned that I is equal to the square root of -1. So if I square I, I'd have to square the square root of -1. And that would leave me with -1. And a complex number is just the combination of a real number and an imaginary number. So it's just written as a plus bi. Now, our fundamental theorem of algebra says if a polynomial function of degree n, or a polynomial function of degree n, is going to have exactly n zeros in the complex number system. So if it's a degree 3 polynomial, it's going to have 3 zeros in the complex number system, meaning not all of them not all of them might be real numbers, but it might be a combination of real and imaginary numbers. All right, our linear factorization theorem says if f is a polynomial function of degree n, then f has exactly n linear factors. So I just want to recap what those last two guys mean. So if we go back to that front page a second. Alrighty. We had a degree 3 polynomial function. We did end up with 3 zeros. Now, in this case, they were 3 real zeros. None of them were imaginary. And we were able to write it as a product of 3 linear factors, meaning all the x's are to the first power. So that's what those two things we're talking about. And then the last thing is our conjugate zero theorem says if a plus bi is a zero of a polynomial function, then so is its conjugate a minus bi. So they occur in pairs. The a part stays the same. It's just the operation between the real part and the imaginary part switches when you have the conjugate. So if I'm telling you one of the zeros of our polynomial function has 2 zeros, one of them is x equals -5 minus I radical 2. We want the other one. The other one is just going to be its conjugate. So we're going to keep that real part as -5. We're going to switch the operation to plus, and then just write I radical 2. And that's all it takes to write a conjugate. So now I want us to write this polynomial as a product of linear factors. So check this out. One of the zeros is x equals -5 minus I radical 2. And if I want to create a factor for that, I'm just going to have to move these two terms to the same side of the equal sign as the x. So to make that happen, I'm going to have to add them both over. So it looks like this. And if I do the same thing with the other zero, move those two terms to the same side with the x, what I'm doing is creating what are called linear factors. So when I write my polynomial as a product of linear factors, it's just going to be f of x equals, and it's going to be x plus 5 plus I radical 2 times x plus 5 minus I radical 2. And notice the x's are to the first power, so that is why this is a product of linear factors. So now we're going to write this as a polynomial in standard form. So what that means is we'd have to multiply these two things together. And since there's 3 terms here and 3 terms here, that would require 9 multiplications, a lot of distributing, combining like terms. You could certainly do it that way, but I want to show you guys a somewhat more efficient way to do it. So let's go back to our zeros. We started with these 2 zeros, right? Now I could write this as x equals -5 plus minus I radical 2, just to combine these two together. And if I take this equation and add the 5 to the other side, I'm going to have x plus 5 equals plus minus I radical 2. So what I'm doing is I'm isolating the imaginary part. Now, to make the radical go away, and to make the I go away at the same time, what we're going to do is just square both sides of that equation. So if I square the left, I got to square the right. And on the left side, if I square that binomial, I'm going to get x squared plus 10x plus 25. On the right side, we're just going to do these three things one at a time. When I square plus or minus, it becomes positive, so I'm not going to write anything. Squaring I gives me I squared. Then squaring radical 2 just gives me 2. Now from above, we know that I squared is equal to -1. So this is just going to be -1 times 2, which is -2. If I add that -2 to the other side, I'm going to have x squared plus 10x plus 27 equals 0. So now I have my quadratic equation that would have these two guys as its zeros. So that means I can write the function as f of x equals x squared plus 10x plus 27. And that would be our polynomial in standard form. Okay, moving on to problem number 8. We're told that we have a degree 4 polynomial function having the following zeros. So x equals -3i, x equals +3i. So those are conjugate pairs. And then we have x equals 5/2 with multiplicity 2. Now, this x equals -3i can be written as, let's call it f of x first. We could write that as x plus 3i. When we do that, all we're doing is just adding that 3i to the other side of the equation with the x to create the factor. So if I do the same thing with the second one, I'd have to subtract it over. And then with the x equals 5/2, we don't want to write that as a fraction. So what we're going to do is multiply each side by 2 to get rid of the fraction. Whoops, equals 5. And then you could subtract the 5 over. So it's on the same side with the x. So 2x minus 5 would be the factor for x equals 5/2. Now I'm writing this as a linear factor. It's 2x to the first power, so it's linear. But because it has multiplicity 2, that means the factor is occurring twice. So it's the linear factor, 2x minus 5, 2 times. All right, now what I want you guys to do is pause the video, see if you can multiply this all out the right way, put this guy in standard form. Just as a reminder, you're going to get an I squared in your work. I squared gets replaced by -1, so your polynomial in standard form should have no i's in it. All right, pause the video, see if you can give it a shot. All right, welcome back, everybody. Let's take a look here. So when I multiplied x plus 3i and x minus 3i, I got x squared, outer and inner cancel, minus 9i squared. The I squared is equal to -1, so that's like minus 9 times -1, so it becomes plus 9. And over here, you just have to square that binomial, giving you these three terms. Then lastly, you just have to distribute these two terms to those three terms, giving us these 6 products. Combine the like terms there on the x squareds and got that as my final polynomial function in standard form. All right, last one we're going to do in the video is number 9. Now you might be thinking, oh, this seems not too bad. It's just a quadratic, just finding the zeros. Now, if we try to set this equal to 0, it's not going to factor. So what we're going to do is we're going to just review using the quadratic formula. So we're going to set our function equal to 0. We're going to write our quadratic formula down. X equals opposite b plus or minus the square root of b squared minus 4ac all over 2a. And I want you to pause the video and see if you can just do that on your own. Simplify as far as possible, and we'll go over it in a second. All right, welcome back, everybody. So I substituted the numbers. Just be mindful when you do this. You should be putting the numbers in parentheses, particularly negative numbers, because if that were a -8, you definitely want that in parentheses before you square it. So in the radical, we're going to get 64 minus 76 is -12. Then we're going to simplify that radical. So we have a negative in there, so we're going to get an imaginary out of that. So it's going to become I, and then we could break the 12 down as square root 4 times square root 3. making it look like that. Square root of 4 is 2. So now my problem looks like this. And since both of these terms in the numerator are divisible by 2, you just divide it by 2 one at a time. Negative 8 over 2 is negative 4, and 2 over 2 is 1. So that means the final answer can be written as x equals negative 4 plus minus I radical 3. So we have two imaginary roots. They are complex conjugates. And in this space over here, I just wanted to show you another way to solve this quadratic equation. It's called completing the square. We could abbreviate it that way. So completing the square will always work, just like the quadratic formula. And to complete the square, what you want to do is isolate the quadratic and linear term. So you're actually going to move the 19 to the other side. And to complete the square, what we want to do is make a perfect square trinomial for these two terms. So to get that third term, we're going to just divide the 8 by 2, which is 4. 4 squared is 16. And we're going to add that 16 to both sides. So I'll highlight that in red. And now on the left side, we have a perfect square trinomial. So that factors to x plus 4, x plus 4. So I'll write it this way first. In the same step, my right side is going to add up to negative 3. But this can be written as x plus 4 quantity squared. So now to solve for the x, we're just going to use the square root property. And we're just going to take the square root of each side. So when I square root the left side, I'm going to get x plus 4. When I square root the right side, I'm going to get plus minus the square root of negative 3. Square root, don't forget the plus or minus. Now, the square root of negative 3 is actually I radical 3. It's imaginary. So I could rewrite this as plus minus I radical 3. And lastly, what we're going to do is just isolate the x by subtracting the 4 to the right side. And lo and behold, we get the same solution that we did by using the quadratic formula. All right, so which one is better? Well, completing the square is only good if the leading coefficient is 1 and the coefficient of the x is an even number, because you do have to divide it by 2. So if that's an odd number, you're going to get some fractions in this process, and you'd probably be better off using the quadratic formula. So I just use this when it makes sense to, and this you could always use no matter what. All right, guys, that wraps it up for this video. Hopefully you enjoyed it, and I will see you next time.